Hello, everyone. Let us continue with reflection and refraction of light. We finished part one. Now we're going to part two. We're talking about the mirror equation and thin lens equation from the Katz book, volume 2. As we said, we did much of this earlier to some degree or another with part one, dealing with reflection and refraction of light. This is part two. We're going to do these 4 problems from the Katz book. Chapter 17, pages 1214 to 1217, problems 36 and 55, and chapter 38, pages 1258 to 1266, problems 55 to 76. Let's try problem number 36 from chapter 37. So problem number 36 from chapter 37. This, very much of this is, if not all of it, at least, I mean, I've done other things to it for the solution of the problem later on, but very much of this, if not all of it, is from Dr. Katz's brilliant work and from people who are developing answer keys for this. Well, for problem number 36, they're saying something relatively basic. From Dr. Katz's book, chapter 37, problem number 36. It is saying, derive the mirror equation, 1 over d sub 0 plus 1 over d sub I equals 1 over f for a concave mirror. It's that simple. Well, you could certainly do that. I just wanted to leave this up here a bit, you guys, when we're doing this, and let's talk about it a bit. What's going on with the concave mirror? Well, they tell us various things, and we'll get to talking about everything that we need to talk about regarding all this. But we're saying basically, here's a concave mirror for you. Here is an object of height h0. Eventually, there's going to be an image, and the image is going to be of height hi, but inverted in this case. So what's going on here? Well, you got h0. Some light goes this way and, comes this way, bounces off. It is right in the middle here. So it's like it's coming off a mirror that's flat, at least in that particular place. There is a place where that will happen. And from the top here will go this way, and it'll be the top down here when you go further away. The further away the light travels, you're talking about similar triangles here, it's going to be a bigger magnitude. Hi is bigger magnitude than h0. There is also the idea that you're going this way, and parallel to it, something will fire out, and you'll also get down to the hi. Talking about the focal point where these two, at this point you have the focal point right here, and you will say, okay, well, what is that? How does that all work? Well, through the focal point, when it goes through the focal point, it'll go parallel, and that's your situation. So here's the distance associated with the focal point, you guys. And so let's see what we can do. I mean, let me erase this. We already wrote it. You wrote it down. You always come back to it and see about what problems I'm trying to speak, and we'll take it from there. So let's see what we can say here. And again, I like, Dr. Katz's choice of language, calling image distance d sub I and calling object distance d sub O. And that might have been, did I miss putting a d sub O on there, guys? Didn't put, oh, yeah, actually, there is a d sub O. It's up here, actually. Object distance d sub O, image distance d sub I, distance associated with the object distance associated with the object, d sub O, distance associated with the image. Different books potentially use different terminology, different symbolism, different labels for what these are. So follow Dr. Katz's language on this. Anybody obviously in the book using for the particular class that we're working in and is doing the calculus-based version of the course associated with electricity and magnetism, and we're using Dr. Katz's book, obviously this is fully consistent with everything that is supposed to be said. I mean, we know this is the language we're familiar with. If you're taking the non-calculus version of electricity and magnetism, you can still use this. The bottom line is just get the right answer. The terminology used in the non-calculus version is, you know, the P and Q. P for the object distance, Q for the image distance. The mathematics is identical. Some of the, you know, the symbolism can be different, as we have said. Okay, so with that in mind, let's try to take a look at some of this and proceed. Okay. Well, deriving the equation, basically, guys. Let's see how they went about it, and let's see what kind of commentary we can give regarding everything that's going on here. According to the language here, if this is going to be F, if you double F, you get to the radius of curvature. And the radius of curvature, capital R, would be located here. So this would be a distance F, and that'll be a distance F. So if this whole distance is R, half of R is F, and F is equal to R over 2. So let's see what we have here. We are told it is fine to deal with absolute values and or just positive quantities, at least as far as magnitudes are concerned. We do know that the tangent, and we're talking about two similar triangles, a big similar triangle, right? A big triangle, relatively big triangle, and a relatively small triangle. They are right triangles. There's a theta, there's a 90 degrees, there's a 90 minus theta. There's a theta, there's a 90 degrees, and of course there's a 90 minus theta there. They're similar triangles. If that's the case, the tangent of theta is h sub 0 over this distance. For this one right here, small rise over small run. The small run is d0. So it's h0 over d0. And the other one is big rise over big run. Well, the big run is di. Okay, looks pretty good. And tangent of alpha, this guy right here, is the run. Well, here we got to be careful. This run right here is F, but you know, yeah, okay, so yeah, that's the run, and this is alpha right here for the tangent of alpha. To try to get the tangent of alpha, but you know, it could be an interesting situation to try to get this. Now, this, pretend it was a straight line. I mean, it doesn't. I was trying not to hit the symbol d sub I, and by doing that, I kind of made a curved line here. But this is a straight line right here, so just go from here up to here, then rise up to here. Well, the rise from here to here is hi. That's the rise from here, you know, from here to here. That's the rise of hi. The run, F is this whole big thing minus what's going on over here. So we got to figure out, we got to talk a little bit about that. Okay, so you got that right there. Tan of alpha is equal to, now let's see, is there a way out to kind of make this thing happen? So there's a couple ways we could have gone. Okay, yeah, maybe there is a good way to go here. There's nothing wrong with the logic of what I'm saying here. It's just not necessarily convenient. You're going to have a hard time finding out what that distance is from the curve right here all the way to this, you know, perpendicular distance straight down, this perpendicular line segment. Perpendicular line segment coming down perpendicular to the ground here. And this curve right here, from here to here, Yeah, I mean, there's a lot you could say. Well, I'll tell you what. Maybe there's a way out of this thing. If this right here is alpha, I'll write it here as well, guys. I'm not sure that's the greatest idea in the world, but okay, I'm doing it. That's alpha. If that's alpha, the tan of alpha, well, look, wait a minute. This thing runs here. These are two parallel lines. This is a transversal cutting two parallel lines. Corresponding angles are congruent. I'll make a long story short. This is also alpha. That's also alpha. You want to get the tan of alpha? Go H0 divided by this length. Well, that's interesting in its own right. The image, the whole object distance is DO, and to go from here to here, as it goes this way, you know, from here, you know, from here all the way to here is the same as from here to here. That's F. So what we have here is, this is F right here. This is also F right there. Go all the way across like that. I mean, that's also F. The whole thing is D0. D0 minus F is this. That's D0 minus F. That's this guy. This is H0. That's a good way out of the woods without having to go down here and maybe figure something out or maybe not figure something out. So you've got the tangent of theta, and that's going to be H0 over, well, here we go. I mean, it's D0 minus F. A number of ways to write that. So you basically got that. And, you know, what else can you say? Okay, well, they're trying to kind of say a couple things here. So let's just say those couple things. They're saying, can you do it here? Can you find some kind of argument this way? You know, I'm looking at it. It's F, HI over F. Actually see where that's going here. It just, for some reason, it doesn't strike me that it's a good idea, but maybe I'm looking at, just see actually how this thing works. Yeah, F was written there. A is there. Yeah, they're saying, you know, perhaps they're saying that the curvature is not, you know, not going to be much of something to pull it away from it. Or perhaps they wrote it down wrong, or I copied it wrong, or I thought it out wrong. But I mean, I think it's, we can kind of say that that distance F is close enough to the adjacent to the angle, and the height HI is what it is. Something's up here. So I got to say HI, let me just follow that. Somehow I think, if I remember how I looked at it when I copied it down, they may have copied it down wrong. My suspicion is this, that this turn right here is not something that's going to be significant as far as this is concerned. This is definitely the focal length from here to here. That's the focal length. They're saying essentially, perhaps maybe they're just saying it approximately, the angle alpha, the tan of the angle alpha should be pretty close to something like that. It shouldn't be too far off. So let's go with that. Let's let it go. They're letting it go, and I trust their judgment, so I'm going to let it go too. We got to that, and we're trying to arrive basically, guys, at the whole situation here. At the end of the day, is we're trying to arrive at 1 over D0 plus 1 over DI equals 1 over F. And that's where we're trying to go. So let's see what we got here. We can see Yeah, that's where we're trying to go. Let's see if we can get there. Well, you know, we already said this, and we said that this is at least approximately right. If f is not too far, you know, if f is not too much bigger than hitting right to the curve right here. The curve right here, like I said, this is probably more exaggerated than anything. And the way this is going to happen for all the reflections to take place, we should be okay looking at it like this. At least that's the argument that's being presented to us. I think it's believable. I mean, it's believable at least as an approximation. So if that's the case, you got two things looking like that. What do you want to say? Well, you can say a lot of stuff. I mean, you can basically, I mean, if they're equal to each other or very nearly equal to each other, tan alpha equals tan alpha, H0 over D0 minus F equals HI over F. So somehow the F is in there, you know, and we're taking it to say that if you're going to go this distance or going to go all the way to here, we'll say it's okay. We'll say they're equal, or very close to equal. Hence, you can go here. True. Divide by HI on each side. You got H0 over HI equals D0 minus F equals 1 over F. Pretty interesting. We know just the way that rays travel. You can clearly see that here. The ray travels, and the height associated from where it travels behaves according to the rules of trigonometry. Trigonometry is satisfied here. It's also satisfied here. If it's a longer run, there's going to be a larger rise, a proportionately longer rise. What does that mean? Well, if you ran twice as far, if the image distance is if the image distance is 3 times further away than the object distance was, the height associated with the image is going to be, regardless of sign, in terms of magnitude, the height, the size associated with the image is going to be 3 times the width, 3 times the height, 3 times everything. If you ran 3 times longer for an image distance, then the height is going to be, in terms of magnitude, 3 times taller. So it obeys with the trigonometry. So what we got here is HO, object height divided by image height. Object height divided by image height is proportional to this. If the ratio of object distance to image distance is 1/3, then the height of this is 1/3 the height of that. And it obeys all the trig. I mean, the big thing here is, let's at least, you know, look at this. I mean, I don't want to draw too much on here, guys. It's almost overwhelming as is, but here's a triangle. Here's another, here's a smaller triangle. Here's a small triangle. Here's a big triangle. They're similar triangles. If the run for the image associated with the bigger triangle is 3 times the run that it is associated with the object distance, then the height will be magnitude 3 times the height that the image distance then for the image will be 3 times the height than the object height was. Okay, it's all about the trigonometry. So we can believe all that. We can write all this. You can write the proportion either way. You can go HI over HO equals DI over DO, or you can go HO over HI equals DO over DI. No big deal. Well, okay, that's kind of a good thing. I mean, we got, and again, we said here there's an approximation here. This is probably well exaggerated, so the distance indeed, the distance of F, when we're talking about, you know, this right here being definitely F, and this right here not being much of a difference, so I can kind of use that proportionality when we're doing it, as I've said numerous times already. So if that's the case, HO over HI is DO over DI. Let's deal with it. DO over DI is DO over DI is the same as HO over HI equals 1 over F. All right, we got to here. It's looking pretty good. See what you can do. I mean, multiply by the quantity DO minus F on each side, and you got DO over DI. You got DO over DI just by itself. Multiply by the quantity DO minus F on each side. Okay. And I guess from there we gotta see, are there ways we can deal with this? Well, you can basically you can write a whole bunch of things here. Let me just make sure everybody's agreeing with what I'm about to write. Pretty fast move that's kind of made on this thing. I may want to go a little bit slower, guys, when I'm looking at it. Okay, I got this. Right. We got that. Right, and then they multiply by F. You can multiply by F on each side. And what you end up getting is multiply by F on each side. So you got okay. Then what we're going to do is, why don't, see exactly what they might have done here. Add an F on each side and write it a little differently. So you got DO over DI times F, add an F on each side, set it equal to DO. Well, I'll tell you what, yeah, that's true. There's no, the math is valid. If we're believing the assumptions that we're making, everything's fine. True, that's just a true statement. F is the same as DI over DI, if you want to write it that way. So you can, I mean, basically when I got F equals DO, and F is the same as DI over DI. DI over DI is 1 times F is DO. So you're looking at something like this. Stuff's basically easier done than explained sometimes once you got the mathematical assumptions in place. But you got right here, and this can be written in different ways, of course, as well. But let me so we got this. However you want to write this, you can write it another way. The way I have it in my notes, just to kind of keep it consistent, you guys. For whatever, I put this over there and put this over here. I just interchanged, did the commutative property, and just said, look, for whatever that's worth, I don't know that it's the most significant aspect of what we're doing here, but let me stay consistent with the notes, so at least when you look at it, there's full consistency. You got F, and you got it equal to DO. Okay. Well, okay, so we got something like this. Pretty straightforward stuff from there, guys. Let me see here. Now we got We got a lot of stuff. I got to erase a lot of stuff, though, unfortunately. Let's see. But we've run kind of the run through everything that we want to run through. Hard to determine how much you want to erase sometimes, I guess. Well, let's see what we have. So we're looking at this, and we got it to here. We're all ready to here. Can we do something here? I mean, well, yeah. I mean, I think there's a number of things we can do. I tell you, I don't even. Yeah, what I said is true. I tell you what, it's just striking me pretty big time here, guys. This would have been maybe an easier move if you'd have gone DI rather than DI over DI. You could have gone DO over DO to also make it happen. Man, sure looks like it's a lot easier to do it that way, to be honest with you. Let me, I don't know, almost break ranks with the whole thing when they actually do it. I've seen different ways to go about it. First of all, this is completely true. What I'm about to show you is also completely true. Look at this right here, and instead of DI over DI is equal to 1 times F, because F was by itself. We did all the stuff we did, and F turned out by itself. Well, anything over itself is 1 times F is still F. Yeah, I know. Why don't you say DO over DO? And watch what I'm about to do. Maybe it's a little easier. There's nothing wrong with this. If you do the mathematics here, you will solve this. I'm almost thinking it would have been a little bit easier. And again, my notes actually do it exactly just like that. Just like that. But instead of DI over DI, which is equal to 1, it's also true that DO over DO is also equal to 1. And this is DO over DI as we were solving this stuff. And we got DO here. Tell you what I'm going to do. Why don't you divide by DO on each side? Divide by DO on each side. Why don't you factor an F out of here? Why don't you divide by F on each side? Again, this is not the only way to go about this. If you believe the assumptions that we're making, it works. And there it is. You're done. You could have stayed with DI over DI. You know, the gymnastics that you'd have to do with it, not a whole lot different. Could have factored, you could have taken this thing, and that's how I think I did it in the notes. I just thought that was a lot easier. That'll get you right here. But you could have gone here, taken an F out of there, and you've got a common denominator, so you add the tops. You take an F out of there, you've got you do the reverse of distribution. You factor out an F out of there. You got a DI right here, DI on the bottom, and you got DI plus DO right here, and all of that is equal to DO. Divide by F on each side, and you end up getting DI plus DO over DI equals DO over F. Divide by DO on each side. Divide by DO on each side, you got 1 over F. That's this guy. I put this guy on the right over to the left. Divide by DO here, DO, DI, and you got DI plus DO. This goes into that and goes into that. Here, as it distributes into there, the di's cancel out, and you got 1 over do. As the same thing, if do di goes into di, the di's cancel out, you got 1 over do. As this do di goes into here, the do's cancel out, you got 1 over di. Yeah, there's no difference, guys. There's no difference. I just figured, at first glance, on second glance, rather, it just looked like it was easier to come right to here if you did what I just did. I just showed you both ways you could look at that. So that is 36. Let's look at 55. 55 is a great problem. Just asks us a lot of stuff, and we're going to take it from there. Problem number 55. An object 3.50 centimeters high is located 18 centimeters in front of a convex spherical mirror that has a radius of curvature of magnitude 8 centimeters. What is, A, B, C, D? A, what is the location of the image? B, what is the magnification of the image? C, is the image upright or inverted? D, what is the height of the image? Okay, that's a whole bunch of stuff. So let's take a look at it. A lot we know, a lot we remember. See what we can say here. Should be pretty basic stuff. And like I said, all the notes will be available to you guys. If you're in my class, I have the notes available on Canvas, and they'll scroll at the end of the video as well. So when you look at the video, you'll see it that way as well. Okay, let's take a look. It is a convex mirror. The mirror is convex. It's diverging. It has a negative focal length. So let's look at a few things. We know the language they're speaking. We know the basic stuff they're trying to say. So let's see what we can say about it. Okay. Problem 55, and it runs the gamut. They're talking about just read it verbatim, I guess, again. An object 3.50 centimeters high is located 18 centimeters in front of a convex spherical mirror that has a radius of curvature of magnitude 8 centimeters. A, B, C, D. A, what is the location of the image? B, what is the magnification of the image? C, is the image upright or inverted? D, what is the height of the image? The mirror is convex. It's diverging. So they use capital R for the radius of curvature. I've used small r in my notes. One or the other is fine, you guys. It's negative r over 2. The focal length is negative 8 divided by 2. The focal length of this spherical convex mirror, this diverging mirror, is negative. Diverging lenses and diverging mirrors, diverging lenses and diverging mirrors have negative focal lengths. Converging lenses and converging mirrors have positive focal lengths. Okay. The equation is what it is. We take it to be this. And let's see what we can do. I mean, we're told we figured out that F was -4. The object was 18 centimeters away. I don't know what the image distance is, but the rest is a mathematical problem at that point. The rest is a mathematical problem at that point, guys. If you're going to do this thing, if you're going to work this thing, how are you going to solve for DI? The way you're going to solve for DI is 1 over DI, leave it as is, subtract DO on each side, and DI is going to equal the reciprocal of this. Really? Well, what is this? We'll get a common denominator, DOF. So what you get is, on the bottom here, you got DOF, and just DO right here. And over here, you got DOF, you got an F on top over here, and the whole thing's going to be over 1. And keep wheeling and dealing, guys. You got DO minus F over DO times F over 1. Well, it's quite the dance, guys, but we got to it. Here it is. At the end of the day, pretty interesting how that works out. I mean, so you go here, and you're basically saying that DI is going to be DO times F over the quantity DO minus F. Great. What does that mean? Well, I mean, it means just what it says. I mean, at that point, you go for it. You say, okay, what's DI? We just said DO, the object distance, was 18. The focal length was -4. The object distance was 18, and the focal length was -4. Go for it. -72 minus a minus is plus, +22. Let's see what we got. I mean, at the end of that, there's a lot of ways to go here. And the way I got it, yeah, it's the same thing. I had 36 over -11. 36 over -11 is -3 3/11 centimeters. That's -3.27 centimeters. So that is the image distance. So A is going to be, there you go. That's A. That's the image distance. Image distance is negative. That's a virtual image. If the image distance is negative, that's for sure a virtual image. The image distance is 3.27 centimeters behind the mirror. B, what's the magnification? Magnification is HI over HO, or negative DI over, so let's see here, guys. Let me kind of go. That was, so this is A. Doesn't look any better, guys. I'm sorry. It's almost so exaggerated, but just kind of get rid of some things and start writing some stuff down here, I guess. We know a lot. We can always go back with the film. We can always go into the notes as well. At A, we talked about the image distance being -3.27 centimeters. Okay, so we said that. That's A. At B, they talked about, what's the magnification going to be? Well, the magnification is HI over HO. Simple as that. And that's equal to negative DI over DO. And that is negative 3.27 or negative 72 over 22. Negative 72 over 22. Divide numerator and, multiply by 1/2 on top, multiply by 1/2 on the bottom, it's negative 36 over 11. So this is negative, a negative, so negative DI, negative of a negative 36 over 11. DO is 18. Now, why did I leave it here? A lot of times it's easier to do some of the mathematics if you've got fractions. The cancellations happen. A little more easier to visualize. That's up to you. Do you want to put negative 3.27 centimeters? The whole thing up here go, right here, go negative 3.27 centimeters. That's what that's equal to approximately. Negative of a negative is positive. Negative of a negative is positive. 36, negative of a negative positive. 36 over 11 divided by 18 is 2 over 11. M equals 2 over 11. That's equal to 0.182. So the magnification, we did the whole song and dance. We got 2 over 11, which was equal to roughly, this is the most exact, actually, the fraction, but that's okay. Just get into a strong ballpark of where this is. You got this. C, M is plus, it's a positive magnification, guys. It's an image. The image is upright. It's a virtual image, but it's an upright image. Image is upright. Okay. That was C. Make sure I'm consistently with it. Okay, the image, yeah. What is the height of the image? The height of the image, good question. We know the magnification. If they told us the initial image, the initial object, the object itself was 3.5 in height. That's all you need. With all that you have here, it's a set deal. We know that it's HI over HO. Yeah, that's, the 0.182. The 2 over 11 is the 2 over 11 is the 0.182, which is 2/11. Might be easier to look at that way. And we also know, 2/11, which is the 0.182, and the height of the image over the original height. Straight out math problem at that point. Cross multiply and do the equations here. You got 11, cross multiply, go this times this is equal to that times that. 11 HI equals 2 times 3.5, which is 7. HI equals 7 over 11. 7 over 11 centimeters, which is roughly 0.636 centimeters. So with this right here, let me just, it's a horse apiece, guys. Where do you want me to stop with this? So we were here. Yeah, we got this. We said it was upright. So there you go. You could also write it like that. We did it from here. Remember some older stuff. We remember a lot of stuff. But bottom line is it's here, and it's here, and this is D. And this is D. Okay. Looks good, guys. Let's go to chapter 38, problems 55 and 76. Let me just... Okay, everyone, let's continue. Let's stay with Dr. Katz's great book, Physics for Scientists and Engineers, Foundations and Connections with Modern Physics, Volume 2. Dr. Deborah M. Katz, brilliantly done book, and let's stay with that book. Let's go for second, we're in Volume 2 of the Katz book, Chapter 38, Problems 55 and 76. Those of you that are taking my class, obviously, with the Katz book, this is fully, this is for anybody, I guess, that wants to learn this. This is some decent material to be looking at, especially useful for us in the calculus version of electricity and magnetism. Though many of these problems won't even involve calculus sometimes, so they can be, many people can use these. Let's look. Chapter 38, problem 55 says, an object is in front of a diverging lens with a focal length of negative 15 centimeters. The image seen has a magnification of 0.400. A, how far is the object from the lens? B, if the object has a height of negative 10 centimeters because it points below the principal axis, it is inverted, what is the image height? What is the image height? So how would that look? Okay, so pretty straightforward. All right, well, we know a lot, guys. We know that the equations, the mirror equation and the lens equation, they use the same equation, essentially. You just have to be careful what you say about focal lengths. Negative focal lengths pertain to diverging lenses and diverging mirrors. Positive focal lengths pertain to converging lenses and converging mirrors. One of the main, among the main things to be looking at. There's other subtleties when there's a combination of two lenses. We have to be very careful there. You've seen that with earlier work. Part 1, we've talked about that. Part 1 of the discussion related to the mirror equation and the thin lens equation and reflection and refraction. So we already talked about that in part 1, some of the subtleties, some of the more complicated matters that can take place. Well, they're saying a bunch of things to us, so let's just talk with them regarding this. For 55, we know that magnification, based on what we've already said, is this, which is equal to that. We know that 1 over f equals 1 over d0 plus 1 over di. They're telling us it's a diverging lens. Well, that's not really the matter right here, but it is going to have significance here. It's a diverging lens, negative focal length because of that. Associated with a diverging lens, we're talking about a negative focal length. Let's see here what we can say. There's a lot right there. We could say for this, m is hi over ho, which implies if you multiply by ho on each side, hi equals m ho. Pretty basic move. If that's the case, what's the height? Height's pretty straightforward at that point, guys. We're talking about 0.4 times negative 10, they told us that it had an object height of negative 10 because it was placed downward for whatever reason, okay? So you do what you got to do, and you end up getting, when we're doing this whole process, you get HI is basically negative 4 centimeters. I think that was part of it. Let me just look at it to be sure here. Didn't really label A, B, C on some of these, but let's just, or did they actually, for that matter? They did. How far is the object from the lens? If the object has a height of this much because it points below the principal axis is inverted, what is the image height? Well, that's B. Okay. So that's that. So this is B. Let me answer B first, then, I guess, guys. After all these years, guys, I know how to write, but I surprise myself sometimes. All right, so we got B for that one, and that's that. Okay, fine. Doesn't matter what order we get these. Eventually, we just got to get them. Make sure we place the answers, label the answers as they're supposed to be labeled, for what part of the problem they pertain. That pertains to B, so you got the answer. That was B. A is kind of what we're doing right now, and that is essentially saying how far is the object from the lens, and then you're done. Okay, that should be all right. So as we look at it, we got to talk some more. Where we can talk some more is right here. Talk about this right here, and that's of interest because if you know the magnification, there's a lot you can say here. So what you could say is, what's the object distance away from it? You're going to use all three items here. All three items are equal to one another. That plays a big role. So how are we going to do it? So I guess the best way to do it is, you know that negative DI over DO is equal to the magnification. They already told us what the magnification is. If you multiply, and there's a whole slew of ways to go here. If you multiply by DO on each side, multiply by DO on each side, then multiply by negative 1 on each side, you'll end up getting what you want to get. I mean, it's negative 1 times MDO. And that's what we're looking at. So we're looking at the object distance and how that's going to play out. Well, we know that DI, negative 1 times positive 0.4, we know that. Okay. We also know 1 over F equals 1 over DO plus 1 over DI. Okay. Let's talk. 1 over F. I mean, there's a lot you can say here, I guess you could say. You're trying to find here, see exactly, let's go back to what's it. How far is the object from the lens? We're in business. There's a lot of ways to go here. Let's talk. I mean, how far is the object from the lens? Your call on this one, guys. We know what the focal length is. I know I erased it, but we've got it. That's what that is. You can do a lot of stuff here. Let me see what you want to do, what we can do here. I tell you what I'm going to do. 1 over F is 1 over F, and we know that it's a diverging lens with a magnitude focal length of 15 centimeters. Negative 15 centimeters is what the focal length is. So you've got this. DO is DO. This is kind of interesting. Let's talk about it. 1 over DO is whatever it is. 1 over di, is negative 0.4 do. That's pretty interesting. Where do you want to go with this? A whole number of ways to go. Let's just start putting the numbers in there, I guess. 1 over f is 1 over negative 15. 1 over f is 1 over negative 15. 1 over do, I don't know what do is. So I don't know what negative 0.4 do is either. However, tell you what I'm going to do. I'm going to leave the do on the bottom and take negative 0.4 and put it into 1 and get negative 2.5. I'm going to add these two together and get negative 1. I'm going to add these two, common denominator here. One over negative 15 is negative 1 over 15. Whole bunch of ways to go. You can put the negative there or negative here. I'll tell you what do you say you cross multiply and figure out what's going on here? Cross multiply. Do times 1 is do. Negative 1.5 times negative 15 is positive 22.5. Now I'm doing that cold. I may have showed that a little differently in the notes. Doesn't really matter a lot, guys. I mean, the big thing is get this thing done. They're looking for do. And there it is. That's A. That's 22.5 at the end of all that. So, you've got the whole thing here. You saw what I just did. do is 22.5 centimeters. That's A. hi is negative 4 centimeters. And that's it. And that's where we're going. That's where we got all that. Okay, let's do the last problem. And that would be 76. All right, guys, number 76 is very similar to what we had done in the Serway book in the part 1 of this discussion. So let's take a look at it. Let's see how it goes. Should go relatively straightforward again. I mean, it was, you're going to have to kind of make up what an image might once be when you're doing this. So let's see how this whole thing goes. And I go into it quite a bit. I mean, you can look at the film. You can look at, if you're in my class, you can look at what I do in Canvas regarding this that you have. You also see this scrolling. Or actually, no, I don't think for these, they don't scroll, you guys. I should take that back. They're not going to be scrolling, but they are in the notes that we have. So let me try to figure out how we're going to be doing that. Okay, so let me look at number 76. Again, so guys, on all these, I think of the way I'd set these up for both parts of the discussion, part 1 and part 2 regarding reflection and refraction, there's not going to be anything scrolling at the end, but it will be in Canvas for those who are in my class. Otherwise, you're basically you're listening carefully to what I'm saying, and you should be okay with that. The film should be sufficient, and the context of the actual discussion should be sufficient. Here we go. So what we can say here is, for problem number 76, and I'm going to actually, I'll be drawing some of this as well, you guys. For problem 76, it shows an object placed a distance dO1 from one of two converging lenses separated by S is 1.0 meters. The first lens has focal length f1 is 22 centimeters. The second lens has focal length f2 equals 45 centimeters. An image is formed by the light passing through both lenses at a distance d12, 15 centimeters to the left of the second lens. What is the value of d01 that results in this image position? B, is the final image formed by the two lenses real or virtual? C, what is the magnification of the final image? D, is the final image upright or inverted? Okay, there's a lot there. There's A, B, C, D. Let's actually take a look at this and see how it's going to proceed for us. So let me draw this carefully, because like I said, in the solutions that I have actually in Canvas, I don't have this drawn because it's assumed that people have the book. So this actually kind of works better for everybody, I guess you could say, that I will be drawing this on the board, because I don't have it drawn in the notes, because I'm assuming, and rightfully so, I'm assuming that people have the Katz book in the class that I'm teaching, where I'm using the Katz book. But, you know, like I said, not everybody's going to have that. So this works out even better, guys. Just watch carefully what I'm doing. We should be okay. A, B, C, D, quite a bit. We're going to ask you, you know, what is the value of D01 that will result in this image position? Is the final image formed by the two lenses real or virtual? C, what is the magnification of the final image? And is the image upright or inverted? It's two images, it's two lenses. There's some distances here put for us. So let's write it down carefully. I think we're going to be okay. Try to draw something pretty good and then maybe leave it alone so I can do some other stuff without erasing it throughout the actual problem. All right, let's see what we can do. For 76, they're saying essentially we have an object looking like that. It's 2.50 centimeters in height. Let's take a walk. I don't know how long of a walk we're taking, guys. Got to make this somewhat realistic and also be able to draw this. Forgive me, that's not 2 point. That was just, they did not say the height of the object. I'm looking at something else. My mistake here. Right. They don't really, there's no specification on that. That is the object. That's the one specification of this thing. Okay, so here's the object. The real object, I mean, later on we're going to do some stuff to kind of, we got to pretend some of the images are an image, or at least one of the images we got to pretend is an actual object when it's not, but we have to pretend that in a sense to do the problem. That's the object. This is F1, F2. They're both converging lenses. F1, F2. I'm not going to do too much artwork here, guys. This one has a positive focal length. This one has a positive focal length because it's a converging lens. This one also has a positive focal length because it's a converging lens. They're telling us the final image position is DI2. And that distance, that's the final image. You know, so here it's final image position right here, this. They put the dotted line right through the lens because that's where you're measuring distances to the middle of the lens, basically. So you got DI2 is this guy. From here to here, that right there is DI2. It's in front of the second lens, DI2. The two lenses are separated from each other a distance S. A distance S. D01 is the real image distance going to 1. This is the distance of the image going to 2, from 2. All right, I mean, it's an alphabet soup already, guys. But we got what we got. Make sure it's drawn correctly here, guys, when I'm doing it. Yeah, D01, DI2, there's S. This is going to look very familiar with the first film, guys. It's going to look a lot like what we did regarding the first film pertaining to this sort of material, reflection and refraction. And that was the part 1 film. It's going to look a lot like the part 1 film. So let's see where this goes, you guys. And again, sorry, I'm not going to have anything scrolling on the end of either one of those films. But earlier films that I've done, yeah, there is some scrolling that takes place that I thought was appropriate. But here, this is going to work just fine, guys, because even the scrolling may not even help in this instance, because I did not even draw it like this when we had done it on there. But this is for the book. It's assumed we have the book or have access to it, and we can see how we can do something like this. And now I've drawn what's on there for you as well from the book. All right. Not anything, I don't know why it looks that way, guys. I made that a little too heavy, but it's all, here's what we're looking at, and they're telling us, you know, they're telling us a bunch of things, and I guess we're just going to have to do all those things. I could say this much. Just write down a few things that we do know. Maybe it'll help us out. I mean, it'll at some point. We got. Let me just write a few things, I guess. This is 1 meter, the S separating them is 1 meter. So I'm going to say, where can we go, guys? I'll go here. S is 1 meter. Since everybody's in centimeters, it might be a good idea to just convert the 1 meter to 100 centimeters. They're telling us that F1 is 22 centimeters. F1 is 22 centimeters. F2 is 45 centimeters. DI2 is 15. So I'll write some stuff here, guys. DI2 at the end of this whole thing, when this all took place, is 15 centimeters. We're going to have to figure this out. Now, there's a lot we can do. Let's just see where we're going to go. I think that's it. I mean, they didn't tell us a whole lot more, but it did tell us what as we said, what D12 would be. So as we're looking at this, this helps. All right. Yeah, I mean, I think we know what we need to know. I mean, let's just repeat what they're saying here, guys. What is the value of D01? What's actually the distance to the first lens? What is the object distance to the first lens? That's D01. That's A. That will result in the image position that they're telling us. The image position they're telling us is from the second lens, it is, 15 centimeters away, but it's on the wrong side of that lens. So really, if you want to be careful about it, if it's at the end of the day, if it's on the wrong side of that, that should be a negative 15. We'll talk about that when we get to it. We'll make that change pretty quickly. All right, let's. So we're saying a bunch of stuff, guys. Let's just take it when we do this, and see where it goes. Okay, we know this. We've been there. We know this. So down the road, if questions of this nature arise, we are able to take care of it. Regarding DO, we know a lot of stuff, guys. 15 centimeters to the left of the second lens, that's DI2. We got to find what DO is. Well, let's see what we can do. The way this is done now, you got to find out what's going on here. There's going to be the light coming from here is going to go through here, and an image is going to be formed over here somewhere. Somewhere it's going to be formed. Conceivably we could say it could even go over there, but let's say it doesn't. But we don't know. The image can be formed. Let's find that image. We'll call it not DI2, which is 15 centimeters to the left of the lens. Should be negative at that point. But if it's not, let's just leave it for now. We'll deal with it. Let's find what DI1 is. Well, DI1. That's a great question to say here. So you say, I'm going to look at this. The first lens is 22 centimeter focal length. 1 over 22. DO. DI1 is going to be the DO2. This is the big thing. We're going to find the image, DI1, and that's really going to be the pseudo object that's going to hit or that's going to deal with the second lens, and from here, it's going to fire out and give us the image Di2. We're going to get Di2. We're going to get Di2 from this pseudo-object D02. D02 will go through lens 2 with focal length 45 centimeters. D02, it's, the light from D02 will go through the second lens, focal length, second lens of focal length 45. This D02 will go through the second lens. Its light will go through the second lens, and this D02 will give us Di2. Well, this D02 is a pseudo-object. It's really the image formed by the real object going through the first lens. F1, F2. So this one will be put through F2, which is its light, so to speak, and that's 45 centimeter focal length for F2. Let's talk about Di1. We got 1 over 22. We got 1 over D01. That's way, way to the left. That's the real object. That's the real object, D01. And the other one is Di1. The rest is math. Well, yeah, the math itself is pretty fascinating. We don't know. We don't right off the bat know what D01 is, and we don't know what D0I is. Right? We don't know what D01 is right off the bat, and we don't know what Di1 is. So let's see what we can do. You take this, and let's try to solve for Di1. When I solve for Di1, then I have found D02. Wow, okay, well, there's a lot going on here. Let me do some math. Leave it alone, subtract. You got this right here, minus 1 over D01. You guys know the deal. I mean, the way it's going to go is it's going to be when you actually get a common denominator and do the subtraction, you're going to get 22 D01. You're going to multiply this by D01 over D01, and you're going to multiply this right here by 22 over 22. And, so basically you're going to go D01 over D01, 22 D01, 22 over 22, that's 22 D01, so that's fine. 22 is here, and let's just, no, I wrote a little too much on the other one. So it's this. That is equal to 1 over Di1. Di1 equals D02, and that's what I need. If two things are equal, their reciprocals are equal. So you got this. Okay. Now you got to be careful. That's the pseudo object, I guess, but we're trying to get to the end here. All right, let's keep going. let's go with, it's the pseudo object. We're going to go 1 over, we're still doing this. This is kind of ruling the day in very much of what we're going to be doing. So let's stay with that. Stay with that equation I just circled. And kind of just work with it. I got 1 over 45 equals the last image, which is di2. And now we got to talk about that. One over di2. And that's an image. It doesn't matter what you say first. You could put 1 over di plus 1 over do. That doesn't matter. I put 1 over di over here. The object is, yeah, the object is this guy, which is now the do. do2 is this. So 1 over this is do1 minus 22 over 22 do1. Time out. This is definitely true in relation to the first lens, but it's not true in relation to the second. In other words, it's true in relation to the first lens, the distance we got, but then you got to take this distance s, which is 1 meter or 100 centimeters. You go 100 centimeters minus wherever that image was, and if it's real far out, I mean, we'll figure that one out too. But I think the way you got to do it is in relation to that. So we can say, we'll go with that. Let's just say this. Everything's true so far. Yeah, everything is true so far, and this is definitely true, but it's true in relation to the first lens. So this is somewhere. Something's up here. Where is it? What's going on? I don't know. I do know, let's say this thing got over here. Let's say it got over here, 30 centimeters. Well, 100 centimeters minus 30 centimeters is the 70 centimeters distance to here. What if it went over here, real far away, 150 centimeters? Well, 100 centimeters minus 150 centimeters, negative 50 centimeters. Yeah, it's on the wrong side. So even here it works out. So you're going to go s minus that, which is 100 minus that. So in relation to this, in relation to the second lens, this is true. But in relation to, forgive me, in relation to the first lens, this is true. But in relation to the second lens, for you to make it happen, you need do2 to be, in relation to the second lens, you need it to be s minus 22 do1 over do1 minus 22. The s is 100 centimeters. So that's what you're doing. So that's what you need. Well, then you got to try to get a common denominator here. You're going to have to multiply, this denominator is 1, you're going to have to get a common denominator here. And it's going to be, for that do, it's do2. Common denominator multiplied by this quantity, multiplied by this denominator right here, multiply that by that denominator top and bottom, and you got 100 d0 1 minus 22 over d0 1 minus 22. And you got the same thing here. And that was this one. And then this one is d0 D01 minus 22 here. That's not going to change. And here it's minus 22 D01. So it's a little bit of a mess. They always are. I mean, whenever you're doing multiple situations like this, multiple lenses like this. So it's coming out to here. And I mean, and there's a whole, and what else could you say? Well, let's see how, yeah, I guess that makes sense. This is 100 D01 minus 100 times 22. This is 22 D01. Subtract 22 D01 from 100 D01, and you end up getting D01 is equal to 78, 70, because 22 D01 subtracted from 100 D01, 22 D01 subtracted from 100 D01 is 78 D01 minus, at that point, right, minus 2,200. Because you multiplied this out here too, and you got that out of there. And then at the end of the day, you got this, just to give you an idea where everything is. It's a lot here. There it is. That's the D02. And you're going to go 1 over. You're going to go 1 over D02. Really? Well, if that's D02 and you go 1, if that's D02 and you go 1 over D02, you're going 1 over this. If it's 1 over this, 1 over this fraction, you just get the reciprocal of that fraction. This thing goes on top, that goes on the bottom. So this is where it's at, and let's talk. I mean, let's just talk some more then, I guess. There's a lot here, guys, that you are compelled to erase quite a bit. Okay, so there's a lot here. We did a lot. I mean, luckily we've got a film, and we can always go back. And, there's a whole lot going on, so let's keep going with it. Well, put D02, this right here, on the bottom where D02 is supposed to be. When you do that, this fraction on the bottom flips because of the nature of the mathematics, and you look at this thing and you're saying, okay, is there a way to look at it? Deal with the second lens with focal length this much and all this. So, okay, I show a lot of this stuff, so let me, we're here. Everything's going okay. So far, so good. The DI2 is going to be of interest, so you got to be careful. Yeah, here's your be careful. The image is on the wrong end of the lens. The lens should be, the image is on the wrong end of the lens. The image should be over here if it's going to be a positive distance that we're talking about, okay? And have some chance, maybe has a chance, maybe doesn't, of being a real image. It's on the wrong end, it's on the wrong side, it's on the wrong side of the lens. So this thing right here, accurately spoken, should be negative 15. Should be negative 15. So let's talk. Let's go for it. Negative 15. I just made it a plus. Whatever. Some of the ways I did the mathematics, I'm less than thrilled by it. But okay, so you're right here. You're right up here. Absolutely no reason there should have been a negative there, guys. Let me just try to think. D01 really told us that. Right. Yeah, I don't know why I had a negative there. I should have never had a negative there. I'll just make a long story short. I'll just do this. So it's good you're not looking at all the notes sometimes, guys. If you can look at the film here on this, it's okay. You got 1 over 45 is 1 over f. You got the new object. Forgive me. The new object, the new distance. Let me see what we can do here, guys. Try to figure this out. There's an object and an image. The image is at the end of the day on this thing. So let me speak according to that. Di2 is the image, and the Di2 is negative 50. I said that the right way to look at it at the end of all this, you guys. Forgive this, guys. But you got negative 15. Yeah, you're going to have to say that's negative 15, guys. They gave us that, and I said, hold on. We're going to have to see what we're doing. Let's talk their language. You got 1 over negative 15. That is, I can use one or the other here, guys. I mean, the DO is the DO2. And the DO2, or the DI2 rather, the DI2 is the image there, guys. So that's negative 15, the DI2. The DO2 is this thing on the bottom, and if you put all of this, you put this fraction here on the bottom, 1 over that fraction is the reciprocal of this fraction, which at the end of the day becomes, D01. I'm looking at my own notes on this, and I'm less than, I don't know, there's so many ways to do it. I'm not saying one way is necessarily better than the other. I'm less than pleased with how that's working sometimes. So you got this over 78 D01 minus something looking like this. So what we have here, guys, is we have this to here, and you can add, so here you go, add a positive 1 over 15 on each side. Add a positive 1 over 15 on each side. Because you know what? It was negative 1 over 15, or 1 over negative 15 plus this equals 1 over 45. This right here, 1 over 15, is the same as 3/15. 1 over 15 is the same as 3/45. Sorry about that. 3/45. Add those together, you got 4/45. At the end of the day, add a positive 1 over 15 on each side. 1 over 45 plus 1 over 15 is 4 over 45. From here, this is an important point. From here, you can do cross multiplication. And, you know, here we go. I mean, just do a bunch of stuff here, guys. When you actually do it, you're going to get 45 D01. That's this guy. That's this right here, going up this way. 45 D01 minus trying to figure out what they've done here. Oh, I'm sorry. The D01. The D01 is just this. It's just 22. Okay, that was D01 is 22. Okay, that's why the numbers weren't coming out. Okay, go ahead. Go 45 times all of this. 45 D01 minus 990. And then, so you go this times all that equals this times all that. Well, this right here is 312 or thereabouts. Let me see here. Yeah, it is. No, 312 it is. 312 D01. 4 times that is 8,800. There's a subtraction there. Keep doing the job. I mean, you know, keep doing the work here, guys. I mean, when you're dealing with this thing, you know, subtract 45 D01 on each side, and you got 267. I mean, here I got 267 D01. Add a positive 880 on each side. Add a positive 8,800 on each side, rather, I'm sorry. And that's going to be 7,810. If it's looking that way. Yeah, it is. Divide. Yeah, the arithmetic's not the issue. You just got to make sure you don't get tripped up with a lot of the procedure that's going on with this thing. At the end of the day, we got D01, the initial real object that's in front of the first lens, the initial first object, or the initial real object, the only object in reality, the real object that's in front of the first lens is 29.25 centimeters from the front. That's A. That's A. Simple question they asked, you know, as far as it's going to go. What is the value of D01 that will result in this image position? What is the value of D01 that will result in this image position? The value of D01 that will result in this image position is actually a real object that's 29.25 centimeters away from the front. That's this guy right here. That's it. 29.25 centimeters in front of this, about 29.3 centimeters in front of that. Yeah, and you had to do it because you didn't know who anybody was. They told you this, but they said it was 15 centimeters away, but it's not the right kind of 15 centimeters away. It's negative 15 centimeters away. I decided to leave it until relatively late, and then, hey, by the way, yeah, it is 15 centimeters away, but it's on the wrong side. You know, so, okay, we're going to have to call it negative 15 centimeters away when we're doing all the mathematics. Notice you had to do things very abstractly. You had to put in for D02, for the second object, which is a pseudo-object, the D02 would result in an image of D, you know, the D02 would result in the end in an object, the D02, the pseudo-object, D02, would result in an image, Di2. Well, you didn't really know what D02 was, but now you do. I mean, DO, you had to do it symbolically and then solve for it. By the way, what is the final image, just for the record, I mean, this DO2 is what we got. We could actually say, well, we got the DO1, and the DO1 was, as we did this whole thing, just write this, so at least I know where I can see it pretty well as well, guys. The DO1, that's DO1. When you found it to be that, you can go into here and punch out what DO2 is. Nobody asked you what DO2, by the way, I don't think they're even asking us what DO2 was. Nobody asked us that. What is DO2, by the way? What is it? Well, the DO1, we knew what that was, and the DO2, let's see here, guys, exactly where that was. That's the new, that's what we got. So, let me see here. For some reason, I thought maybe they'd be asking us that, but they did not. DO1 is what we got. DO2 is a walk in the park at that point. You could take for DO2, you could take 78, multiply it by DO1 minus 2200, divide it by DO1 minus 22. So you could take this right here if you wanted to find DO2, put in the 29.25, multiply it by 78. Subtract this from it. When you're done, take 29.25 and subtract 22. 29.25 subtract 22 is 7.25. 7.25 into here, there's your DO2. The DO2 is the DI. It's like, what is the, is what the DI that comes out is the DI1. The DI1 becomes, becomes what the DI2, the DI1 and the DI2 were what that was. So they said that. Now, somewhere in here, just out of curiosity, they got to be saying that. Yeah, the DI1 is the DI2. You got to be careful where they're located, though. The DI1 is a distance in relation to here. The DI2, the DI1 is relation to this guy. That's the DI1. The DO2 is in relation to this one. So you got to take 100 minus what this guy was. And that's where you got to be careful. That's where you got to be careful. And that's where we're doing. That's where we got the 100 business. The 100 minus this guy is the DI1 in relation to the first lens. Subtract that DI1 in relation to the first lens from 100, and you get where that image would be in relation to the second lens, and that's DO2. Okay, there's a lot there, guys. There's a lot there. But there it is. B, the final image is virtual because it is in front of the converging lens that created it. The final image is virtual because this thing is in front of the converging lens that created it. If it was real, it'd be on that side, but it's on this side, so it's virtual. The final image is virtual. This is B. The final image is virtual because it is in front of the converging lens that created it. So it's virtual. B is virtual. C. What are they saying here? So you're saying, well, they want to know the magnification. What is the magnification of the final image? How about M equals M1? How about M equals M1, M2? right, guys, you got them. Got it on film. You can always go back, kind of look at what I was saying. There is no real easy way to look at this stuff sometimes. I can almost guarantee that one. B, we said virtual for the reasons we gave. C, magnification. M1, M2. Well, in relation to the first lens, didn't we say that DO, so we said, we said a lot of stuff. We said that DO1 is 29.25 centimeters. 29.25 centimeters, DO1. DI1 is, after the whole, I erased the whole song and dance, but I think we almost have it memorized, even despite how complex it is. What the heck is what, right? We looked at it like this, and that's in relation to the first lens. That's in relation to the first lens. So, look, let's just kind of, I said what I said here. Let's kind of do this. The negative of any kind of the negative of the appropriate image distance divided by the object distance, the negative of the appropriate image distance divided by the appropriate object distance. Well, it's kind of neat. I mean, it's got its own pretty fascinating aspect to it. The DI, the negative DI1, and we'll see what we can do here. Shouldn't have been a negative there, guys. For some reason, I maybe a little careless with the signs. I guess you could say the big picture here at the end of all this is the image distance, 22 D01 over DO1 minus 22. D01 The other one is negative 15, the opposite of negative 15. So it's negative 15, opposite of negative 15 is going to be a positive 15. I just don't like the way I wrote any of this, to be honest with you. But that should be a negative 15 there, but it's going to be the opposite of it. You remember this mess? The 78, D01 minus 2200 over D01 minus 22. For some reason, I don't like, the magnitude of this is fine. The signs are just an issue for me. Right. You got this. So DI1, right, would have been this. over DO. That's the first one. The second one, you have to do it in relation to something else. So you're like the opposite of that, and then you're saying the opposite of the other one. Turns out the signs work out right. For some reason, I just don't like the magnitudes are all right here, guys. For some reason, perhaps I'm missing something. All the magnitudes are fine. I mean, when you go for it. The negative should have been here, and negative of a negative is positive, so it doesn't really matter. There would have been a negative here, and that's it. And this would have been negative of a negative, which is positive. So here there's just one negative in the whole thing. In reality, there should be one negative, and it only should be here, not there. In the end, it doesn't matter. You're going to get the numbers there. Now, when you actually do it, and then you plug in the actual values, you end up getting here we go. You got this times a negative 15. Again, I'm not agreeing with the negative 15. There's got to be a negative somewhere, and there's only one negative. So okay, I'll let it go here, but that doesn't really explain it that well, in my opinion. But there is one negative, and here it is. I can look at the notes again, guys. But at the end of all that, you've got, for a magnification, m equals negative 4.05. That's true. The question of the other stuff that was going on. This is faithful to being the distance in front of the second lens. This is faithful to the distance away from the second lens, and it's a negative. It should be negative of that negative. That should be a positive. Here, there should be a negative too. It doesn't matter. There's got to be one. There's one negative that should be present. I just put it in the wrong place. It should be, but otherwise, it should be the right answer, the way it runs out. You got D01. You plug in, and then, like I said, once you get to here, you can plug into D01 and actually find what the heck's going on. For D01, we said it's about 29.25. Give you an idea what that is. I mean, 29.25. That should, unfortunately, I don't have a calculator on me, but 29.25, if you went 30 times this, you'd get, you'd get 2,340. And if you subtract a little bit from it, you'd still be on the positive side. So this is going to be a positive number here. Divided by this, still a positive number, multiplied by negative. If you had the negative here, the negative times the positive would also give you the negative answer. Bottom line is, there's your answer, guys, when you're doing that. Because it's negative, the final image is inverted. It's a little more than 4 times bigger than the other one. So if I drew it, it'd be off the board, and it would be downward, according to, if I drew some kind of scale to this thing. Not that this whole thing is drawn to scale to begin with, but if it was drawn to some kind of scale, if this is going to be a particular height, what would be the height of the image? Well, the image would be right here, the final image right here. It'd be, go 4 times that, you're down here somewhere. It's in the negative direction. So D is, because of the negative magnification, final image is inverted. That's D. Okay, so just watch out some of this stuff, guys. It's easy. You can see, the DO2 is the DO2 is the DI1, and when you actually did the subtraction, that is a positive answer. This is a negative number, so negative of a negative is positive. This DI1 and this, the DI1 is equal to the DO2, in a sense. Or they are, but you got to watch out the way they're written. This would have been the amount that it is. This is the amount that it is in front of the first lens. This is the amount that this same image, DI1, is this far in front. Forgive me. It's this DI1. This DI1 right here. This DI1 is the amount of distance that the image is on this side of the first lens. If you take this number that we got on top here, right on top, this number on top, if we take this number on top and subtract it from 100, we get the distance that the DI1, which is also equal to DO2, we get that distance, that DO2, which is equal to DI1, we get the distance that it is in front of F2. So we're talking about DI1 and DO2 are the same thing, but the distance, DI1, is the distance on the other side of lens 1. The distance right on the other side of lens 1 from lens 1. That distance, subtract it from, this is 100, subtract this distance, DI1, subtract DI1 from this distance S, we end up getting this distance, which is DI1's distance to get to the second lens. DI1's distance to the second lens. DI1's distance to the second lens, which is the same as DO2. The pseudo object is that same distance, DI1's distance to this. DI1's distance from here was this. DI1's distance to this guy is this distance. DI1 is the same that we're considering. We call it DI1 here. Here we call it DO2, but that pseudo object has to be regarded as a distance not here to here, which is DI1's distance in relation to lens 1, but 100 centimeters S minus this distance will give you this. S minus, this distance subtracted from S will give you the distance that DI1 would be to the second lens. That's DO2. DO2 is the pseudo object's distance to the second lens. DO2's distance located in the same place as DI1, but this number is associated with distance to the second lens. This bottom number is associated with distance to the second lens. This number is the same location, but the number associated with it, the distance associated with it, is different than this because it's the distance to the first lens. Whereas here, they're both the same location. Distance to first lens, and here, distance to second lens, even though they're the same location. Do the math. This right here, again, it should have not been there. It is a negative 15, but the opposite of a negative 15 is positive 15. The negative should have been here. Doesn't matter. At the end of the day, you're getting numbers of magnitude. When you do the whole process, the magnitude of the answer is 4.05, and there was one negative sign in there. So that does work. Okay. That was it. These are never easy to talk about, and frequently you're not going to see them on a very long, if you got an exam that's 30 or 40 or 50 questions long, it just seems like it's a bit of a stretch to even ask one question like this. But it's good to know how to do it. You can see it in homework. You can maybe see it on an exam that would be presented in some other context with a little more flexibility. But certainly when there's a time crunch, likely not to be seen, but it's good to know the mathematics and be comfortable with what's going on. Okay. Thank you so much for your time, guys. Take care.